Can you hear me now? Okay. So I was talking for like a few minutes without anybody hearing anything. All right. So I guess there were some glitches. Nobody could hear me. So let's go back. Oh, okay. We have people in class too. Nice. Hey, Chester.
Hello. Hi. I'm Fred.
So one thing you can do is actually joining via the. I mean, are there other people in the class too?
There are a couple, but we all have our laptops out.
Okay, so one thing you can do is that you can use the computer there and connect to the Zoom. Just use the meeting ID and you can connect it and project it to the room as well if you want to. This is the I just put the meeting ID in the chat. So if you just put it in the meeting ID, you will be able to put it in. All right. So I was saying that what I'm going to do is that I'm going to quickly go over the part that we didn't have to cover last time. So to finish the physical side channel part, then I'm going to pass it to you guys to do the presentation. And yeah, we probably like making the lecture today a little bit short because I'm not feeling very well today, unfortunately. Any questions, anybody, before we get started? Okay, so a couple of things before we talked about physical side channels. One is I'm going to post a Google form about whether you're taking the exam or doing the project. So just to have some sort of, statistics on who is taking the exam and who is doing the who is doing the project. The final exam would be in the exam weeks. Probably I'll give you 2-3 days to take the exam, and it will be from the entire course basically. So it wouldn't be just for the first part or second part. The quiz, which is going to be next week, is going to be just for anything after quiz 1. So just the second half of the course. And the final would be very similar to the first 2 quizzes, but it would be cumulative. So everything would be included. Any questions about the final exam and the project? And then for the projects, I'm gonna also post another thing on campus where just giving you the logistics of what you should submit and what are the expectations and so on and so forth. All right. Okay. So can you see my screen, right? Everybody can see my screen. Can see the slides. Okay. All right. So yes, the next Wednesday would be the last content. Actually, we will probably don't include Wednesday content to make it slightly more easier. So everything we say until next month, like after the next Monday, would be basically your quiz. Cool. Okay. So we talked about physical side channels in the previous lecture, right? So we talked about, how we can do physical side channels, what are the challenges and so on. The last thing that we discussed was the main challenges, and we talked about, interference, device variation, temporal and runtime variation, and sampling rate. And etc. We basically say that, physical side channels is nothing different than any other physical signal that you're receiving, just the band is different. But again, all those techniques that we use typically for physical side channels does include, for any other signals does include in the physical side channels as well. The difference between different types of side channels. So as you remember, I said that we have different types of side channels, including EM and power. There's also acoustic, RF, temperature, etc., etc. Really, the main difference between different side channels attacks is really which of these signals are being used. As I said before, the main 2 ones are EM and power. So basically, because it's much more easier to measure this, and the amount of information available in these channels are much more higher, Typically you see lots of attacks on EM and power compared to the other channels. There are lots of research on trying to find a more unconventional channel. So for example, what has been done so far is things like LoRa or RF modules and things like that, which I think like one of you will present the EM LoRa paper today. So these are like some of the non-traditional side channels where we assume that, we just, have some activities, we get some, for example, electromagnetic emanations. But these people, for example, have shown that what we can do is that do a little bit more complicated stuff and basically create a LoRa-like modulation and so on. There are newer paper even after this paper that shows that essentially the device itself can become some sort of software-defined radio. So depending on the software activity, the attacker can generate any arbitrary modulation. So that's also very interesting. Going back to here, given that there are these, different type of side channels, the assumptions about the attacker capabilities is an important thing. So what is the distance that the attacker can have? What sort of equipments the attacker can use? When we are saying about equipments, we're talking about things like, size of the equipment, the best SNR the equipment can, excuse me, can measure things, the accuracy of the equipment and so on and so forth. And of course, what is trying to be extracted is, excuse me, and what can be extracted is another key issue. All right, so as I said, new side channels is an active area of research, as you will see today about LoRa. There are new papers about power management units as well, and about the excuse me, about the radio frequency and RF signals too. I'll be right back. Let me grab some water. So let's quickly talk about the defenses. So some of the defenses are kind of similar to what we discussed for microarchitectural attacks. But one key thing to remember is that defending against physical side channels are essentially more difficult than defending against microarchitectural. And the reason for that is these physical side channels are being created just because of laws of physics mainly. So you can really not remove them. Versus for things like digital side channels, you can do isolation, or you can, for example, disabling cache and stuff like that. So this is like one key difference between physical and digital side channels. Any question at this point? All right. So we talked about these very quickly last time, but let me just give you a little bit more overview of this. So one thing that can be done is the usage of the software and compilers. It's very similar to digital. The idea here that we want to make the software similar when we are doing two different paths or two different values. So if you want to, for example, hide the key, what we should do is that the amount of side channel signals created by processing one should be very similar by the amount of signals being created by processing zero. And this can be either done in the software level or during the compilation, the compiler can add this additional instructions. There are lots of works of how to do that. Of course, this impose some overhead to the systems and reduce the performance, but on the other hand, gives us the security that we want. One of the key things that we can do with physical side channels is, limiting the signal leakage, especially for example, electromagnetic side channels. Shielding and Faraday cage is one of the key ways of reducing the leakage. For the power, for example, protecting the pins and making sure that the attacker cannot easily measure the power is another way of protecting against physical side channels. Adding randomness is another key way of doing this. This is also very similar to the digital, because similarly, the idea is that the signal that we are receiving and the activity are kind of correlated. So what we should do is adding some randomness to the activity so that, you know, these two becomes decorrelated, right? So there are ways, for example, if you're processing zeros and ones, what we can do is that if we start doing some random activity as well, the attacker will not be able to distinguish this randomness from the original activity. So we can fool the adversary in that case. Again, the downside of this is that we are adding extra overhead to the system, mainly in terms of power consumption and performance. One key thing that is different from digital side channels is that we can actually physically, you know, secure the device, because all of these physical side channels require some sort of proximity to the device. So if we can, for example, put the computer in a safe place and so on, that's technically can improve the security. The analogy with digital side channels is that if we not sharing our resources with unknown processes. So for example, if there is a cloud, we only give access to users that we kind of trust. Again, none of these two are perfect. So there could be scenarios that the attacker one way or another managed to, you know, infiltrate the systems and measure things. And also, as we're going to discuss, for example, in the paper like EM LoRa, as somebody will present it today, you will see that, you know, in order of kilometers, we can actually, you know, measure some side channel signals. So this is actually not easy to protect. You cannot, you know, have a large perimeters and making sure that, you know, nobody can get near to it. Maybe for very high end, like, you know, highly classified, you know, environments and buildings, you can do that. But when we are talking about consumer grade systems, like devices that me and you are using, then this whole idea doesn't make any sense. All right, so let's also talk about covert channels. Before that, is there any questions, anybody? All right. So I see that people in the class also can see me and hear me pretty well. That's good. All right, so let's talk about the last thing before actually jumping to the presentation, and that's covert channel. If you remember last time I gave you the definition of what is an air gap computer. So just to quickly remind you, air gap computers are those computers that any sort of interaction with the outside world through the I/O or the memory is being either heavily monitored or completely disabled. So in other words, this is a device that cannot communicate with the outside world unless it's, you know, a monitor system that actually authorize that device to do that. This is a typical practice in secure systems. Essentially, in most of the companies, most of the laptops that they gave to their, for example, to their employees are either air gapped or at least partially air gapped. For example, if you're trying to, like, you know, hook up your USB device and tries to copy something, you will be blocked or it will be encrypted. So there are some notion of, you know, air gapped computer in most of the even consumer level systems. The main interesting things about physical side channels is that the covert channels with physical side channels can actually, you know, negate this air gapped assumption, because essentially what happens is that through things like power or electromagnetics, the adversary can manage to exfiltrate data to the outside world. So this cannot happen with digital side channels, because the assumption with digital side channels was that we can launch the attack remotely, but the air gap computer is basically trying to, you know, remove that possibility by like, you know, disabling network, for example. But air gap computers cannot help you with physical side channels. So for highly secure systems, actually covert channels using physical side channels is more desirable than digital side channels. Any questions here? Okay. One more thing that are also relevant to physical side channels attacks is fault attacks. So the idea is that we can change the physical characteristics of the device to intentionally create a fault. All right. For example, one of the key area of research and key ideas here is changing the voltage of the systems. If we undervolt the system starts, creating faults and creating errors. And the adversary, by intentionally changing that, they can manage to fail the systems. The research actually here is more advanced than that, and people have shown that, for example, by partially creating faults on the systems, they can even find some secret value in the systems, because only specific bits going to be failed or flipped. And what they can do is basically extracting that information and show that they can find a secret value from that. So creating fault, for example, like creating a really high temperature to the device so that the timings becomes higher and the system eventually fails. Reducing the voltage. In other words, any sort of additional noise that has a significant impact to the systems can create a fault, and that fault either can, impact the availability of the system, so the system can break down, can impact the integrity. Usually what happens is, some of the bits will be flipped. So even though it may not, leak any secrets, but at least the system itself won't operate regularly. And as I said, in some advanced scenarios, confidentiality even can be violated by people have shown that, for example, for trusted execution environments, specifically SGX, undervolting can reveal some secret information. So these are also an interesting line of research, which has been around for a while and is recently also gets some traction again. Some of the examples of these fault attacks, Rowhammer is one of the famous ones. If you haven't heard about Rowhammer, I definitely suggest you to go and read about it, because for the interest of time, I'm not going to go through it. But very basically, the idea is that if we keep accessing a specific line in the DRAM in our main memory, people have shown that accessing this line, for example, will result to big bits being flipped in the neighboring line. So let's say that we are addressing, we are accessing address X. The research has shown that X plus 1 or X plus minus 1 or some other neighbors can actually be flipped just because we are keep accessing this. So there are some, magnetics and voltage relationship between, neighboring lines that keep accessing specific lines will create bit flips on the others. And this Rowhammer attacks becomes very sophisticated these days, that they can specifically target a specific line or specific cell. And people have shown that this can result in significant, security problems. And also there are lots of defenses for Rowhammer, which is also quite interesting. Rowhammer is one of those interesting ideas that have been around for about 10 years or so, but recently, again, this is one of those things that got lots of popularity more because there were new attacks and new defenses. Another things that you usually see for fault attacks is laser or RF injection. So if you have like semi-powerful laser and then you actually inject and you focus your laser beams to the device, people have shown that this could result in some bit flips in the systems. And again, if this attack is sophisticated enough, as some paper shows, this could lead even to confidentiality violations and revealing some secrets. Another area of research about the fault attacks and physical attacks is disrupting the sensors. So we don't necessarily change the data during the computation. What we can do is changing the data during the sensor. So the input itself is faulty. Remember, for example, we talked about adversarial examples in machine learning. That's kind of like disrupting sensors, but this is more a physical way of doing that. So basically what we do is that we either change the physical characteristics of the environment. For example, for adversarial machine learning, we add patches to the image or things like that. But what we can do is also change the sensor behavior, like changing the temperature of sensor or adding another strong source of noise to the sensor and things like that. That can actually lead to fault attacks as well. And as I said, changing the condition of the system, such as, undervolting or adding temperature can be another example for the fault attacks as well. So generally, this is also, as I said, this is an active area of research as well, because there are lots of, different flavors that the attackers can use to attack the systems. Any question at this point? Okay. So one last thing before we move to the presentation is, so so far we just talked about negative things, but an interesting approach to side channels is that side channels can also be used for useful purposes. And this is actually one of my key area of research when I was doing my PhD. And for example, what we did and what we shown is that for the very same reason that we are saying that physical side channels can reveal secrets and leak information about the system, we can use that as kind of a ground truth for monitoring the system as well. So if we just imagine that, for example, we have a device that has some physical side channels emanating from it, right? What we can do is that we can have like a training phase here that we said that, okay, we run a specific program here and we train the system and we get this training or reference phase here. Then during the monitoring phase, what we are doing is we basically comparing the signal with this signal here. And if these two matches, it means that the device is actually doing what it's supposed to do. So the device has not been tampered with, it's not been attacked. But if these two doesn't match to each other, it means that the device is starting doing something else. And that means that the device has been attacked. So for example, think about this so what we can do is that we can use this to find things like memory safety attacks. So if the buffer overflow happens and the device has been hijacked and start doing something else, obviously we're not continue running the same program that we used to. We start running the other program. And so far we discussed that how different programs can generate different signals. So essentially by looking at this, different signal here and comparing it with this training signal here, we can see that, these two doesn't match, and we can use this for protecting the device. So in this scenario, side channels is not a negative thing, so it's actually a positive thing because it can be used as a ground truth or source of information to monitor the system. So this can be used for many different things, for anomaly detection, for profiling, for authentication, and many more. So there are lots of people working on this area and then show that there are lots of different use cases for the systems as well. All right. So any questions about this part? Okay. So just to summarize the things that we discussed about side channels, both in this lecture and previous lecture. So first of all, physical side channels is critical vulnerability. We need to be careful about them. We need to be aware of them, and we need to design our systems in order to be secure against them. Unfortunately, because of the prevalence of more competing devices these days, and the rapid increase of computing systems in more critical systems, physical side channels becomes more and more important these days because maybe 20 years ago we didn't have smartwatch and smartphone with us, but now we have all these things carrying our critical information, and they are available in public, right? So they are actually operating in hostile environment. And now we are opening the door for lots of opportunities for attackers to attack these systems as well. We talked about the defenses. Many of the ideas in the defense kind of shared the same rationale with digital side channels. Some of them are slightly different just because of the nature of physical side channels. But one key thing is that essentially defending against physical side channels is more difficult, because we cannot really remove completely these signals. Okay, so this was just the old slides. So we have class on Monday, so don't forget about this. But I hope that you already watched the video that I asked you to watch about the Spectre meltdown. All right. So as I said, just quickly remind you again before we jump into the presentation. I'll post a Google form for final exam. Don't forget to fill that in. And then I'm going to post another thing about your final projects, what you should do, how to turn it in, and so on and so forth. All right. Any question, anybody? Okay. So let me stop sharing. So who is first going to present today? Let me look at my notes here. Is the video on Bloom Learn Campus World or the website? Which video? The video that I asked you to watch? I think I put the link on the lecture. It's just a YouTube video, so you just have to watch it on YouTube. Okay, so Chester, I guess you guys are first, right?
Yes, I think so.
Okay.
Okay, we have to.
Yeah, you have to mute
So we're gonna
that.
screen share through this computer.
Sure. Can you hear us?
Yes.
Cool.
Okay. So, that's the
Oh,
camera.
it's not on here.
Wait, how do we? Can you fix that?
Oh, we didn't share the screen yet, I think.
Sorry, we thought it was an in-person lecture today, so.
That's all right. That's actually good of you that you came to the class and doing that. Sorry for like late notice.
It's okay. It's pretty cool being up here.
Yeah, we can see you well. So yeah, go ahead.
Okay, so our paper was Get Your Hands Off My Laptop, Physical Side Channel Key Extraction Attacks on PCs by Genkim, Pittman, Tromer. I'm Fred.
I'm Chester.
All right. So a brief overview of our presentation. First, we'll be going over the problem at hand, followed by a little bit of background, and then the 5 attacks that the authors developed in this paper, specifically through the physical side channels, and followed by the evaluation methodology, the results from the 5 attacks, and future work that can be done in this field.
So to start off with the problem that the authors identified, basically electrical noise produced by encrypted related computation produces noise that can be measured on the ground traces of a PC. This allows an attack on basically any surface that can be connected to the ground of a PC. So things like display cables, Ethernet, a human hand touching a laptop, a USB cable, they're all potential attack surfaces where an attacker could touch a laptop or probe the end of a USB cable and carry a device that can measure this potential and successfully steal a private encryption key. So just as a background, side channel exploits, like we've been talking about in lecture, used to mainly focus on small specialized devices like embedded microcontrollers or FPGAs, where the noises that can be measured are very closely linked to the processing going on. And these small embedded devices can also be kind of probed and attacked in like a lab or wherever an attacker wants to take them. In this paper, the author wants to focus on PCs with very high clock rates where measuring these noisy signals is difficult. And there's also many sources of noise. And additionally, they focus on an attack where the attacker has limited access to the PC. They come into a room and they see it for 30 seconds or a couple minutes and they can steal the key instead of probing it in like a lab environment. So as I was talking about, the threat model assumes the attacker can run limited software on the target PC, where they can run what they call a chosen ciphertext attack, which we've also talked about. And the author assumes that there is limited physical access to the device, but this can also be done through like an HDMI cable that goes off into a cabinet or a wall where you might not actually know what it's connected to. And by measuring the noise output by the computer, the attacker is able to successfully steal both RSA and LGAML private encryption keys. So the paper introduces 2 different kinds of an attack. They do an adaptive and a non-adaptive approach. The adaptive approach has a chosen ciphertext side channel attack where they basically extract prime modulus used in RSA encryption bit by bit iteratively. So they use one chosen ciphertext to reveal the first bit, and then knowing the first bit, they can reveal the next bit, and on iteratively until they know every bit. And this is only works with the assumption that you know the previous bits, but it is very successful and very quick. It only takes like 5 or 10 seconds, and they extract the whole private key. Now, the non-adaptive approach can also steal keys, but it just uses the same ciphertext over and over. But it requires a much higher sample rate to see lower level computations done on the CPU. And it obtains individual bits by watching basically how the CPU squares numbers and counting how many zeros show up within the control flow. So basically how the authors set up the attack is measuring the ground traces of a laptop, usually the chassis. And so their basic attack involves a probe wire that is positioned to come in contact with the laptop and then pass the signal on ground through a bunch of amplifiers, filters, and a digitizer before running some signal processing to extract the key. This, yeah, like I said, it's measuring the voltage between the ground and the chassis. And it's done using a ground loop created with a laptop and an amplifier. So they mentioned that for the cleanest results, they want a probe trace that is closest to the CPU where the noise is being generated, and then your ground reference furthest from the CPU in like a kind of a clean, noisy area. And that's just to get the noise that you're measuring to be most correlated to the CPU computations and not things like the switching voltage regulators on the laptop. So just kind of an overview of their signal processing in the attack. They basically take the instantaneous frequency that they measure in the noise, and they can correlate it with the specific bits of the secret key. So some of the signal processing they use is a low pass filter to remove the high frequency noise. They also do FM demodulation around a carrier frequency that they derived just with empirical testing, and a bandpass filter. And yeah, as I said before, they can extract keys within just a couple seconds.
All right, so the next attack is kind of similar in principle in that it measures the electric potential conducted or leaked by the CPU, but this time it's done through the actual I/O cable ports of the computer, as opposed to touching the chassis itself. So since most digital cables, as it says here, include a ground trace with a conductive shield on their I/O ports, all of them are weak to this attack, like Ethernet, USB, VGA, HDMI. All of them have enough electric potential noise determined by the authors to be measured by this attack. And since this is a good attack for like conference rooms or like lecture halls where you plug in your laptop to do a presentation, it is a good alternative attack as well. So the authors found that using the physical measurements taken from the Ethernet cable plugged into the laptop, for the couple of scenarios like the non-adaptive RSA key extraction, they were able to extract 2042 out of 2048 bits of the key over 5 decrypting operations of around 0.35 seconds each. And they were able to brute force and search for the last 6 bits. For the non-adaptive LGAMO encryption, they were missing everything but 3 bits out of the 3072 bits over 4 decryption cycles and search for the rest again. Lastly, for the adaptive key extraction, they were able to get the top 1024 bits of the secret prime over the course of an hour on a Daegling USB cable, which took around 15 kilohertz of bandwidth. And using that, they were able to fully expose the key. So the next attack is also similar in principle, as most of these attacks do focus on the principle of the difference in electrical potential on the chassis of the laptop. For this one, came the name of the actual paper, Get Your Hands Off My Laptop, and that the attack is based on someone's human hand touching the laptop itself. And on the person wearing a amplifier and an ADC that's enough to measure the entire or the fluctuations of the potential on the surface. So by using either a metal object to touch the laptop or their hand itself, they're able to measure the electrical potential. So it's similar to the first two attacks, and the same flaw is being exposed. And the authors also very interestingly noted that this attack is particularly effective in hot weather with sweaty fingers. So very thorough testing there. So you'll notice for the results of pretty much all these tests, the results are identical. And I thought that was particularly interesting. And that like even in the paper, the sections where they talk about their results is like pretty much identical for each test. So there's a couple of reasons for this that we'll go into or we'll briefly discuss after of the experiment. So once again, for the non-adaptive RSA key extraction, by measuring a metal object held in their hand against an exhaust vent or sticking through an exhaust vent to touch the heatsink, they were able to find, or they were able to measure the noise and find 2042 out of 2048 bits of the prime for the RSA encryption over 6 cycles of 0.35 seconds each, exactly the same as before. And for the non-adaptive gamma key extraction, they were able to find 3069 out of 3072 over 16 cycles of 0.1 seconds, so a little more. And for the adaptive key or adaptive RSA key extraction, it was the same again with 4096 bit key and the top 1024 bits being extracted and exposed, allowing the full key to be exposed. So the next attack they did was a more standard one, an electromagnetic attack. This one doesn't require any direct contact, but it requires an electromagnet or EM sensor or EM probe to find a signal, which is then low pass filtered and then amplified using an impedance matched low noise amplifier. It's then digitized and processed by the computer to figure out or to reverse engineer and crack the code. So for this one, the results are once again the same. So bear with us. For the 4096 RSA key, 2042 out of 2048 bits over 6 cycles, and for the L-gamma key, everything but 3 bits was cracked, and for the adaptive RSA, the top 24 bits were extracted as well. The point is basically like we believe the authors just went until they were able to crack the code and stopped there, which is why all of these results are similar, because their testing methodology was similar, and the principle in which they like tested all of these, or the principle of like the electrical fluctuations on the chassis in which they tested all of these on was the same for their test setup. So if anything, I think their test setup was a little bit too consistent. If it was a little more robust, I think more insight could have been gleaned about these attacks, but they had a very like standardized setup and stopped like right when they got what they wanted. So there's one more test, the power analysis attack. Not too sure why the authors didn't do a thorough testing for this one, possibly because it didn't work for the other key encryption or for the other encryption, but I feel like it would have been better to have reported that. But anyways, so for the power analysis attack, it's exactly what it sounds like. The authors measured the current draw fluctuations on the power supply of the laptop in the very low frequency range and the low frequency range and used a 0.5 ohm resistor and measured the voltage drop across that resistor using the MIDAC, which if you did your undergrad at UCLA, you'd be very familiar with. And then they passed that through a low pass filter. So once again, they only ran this, or they only reported on the results on the third test, the 4096-bit RSA key extracting the 1024 bits. And that leads us to believe that the first two tests didn't work and they might not have reported on that. But regardless, those are the results that the authors supplied, showing the feasibility of these attacks, although in very stringent testing conditions. So for physical mitigations that the authors proposed, for the voltage-based side channel attacks, bypass capacitors can be used to short the noisy currents to ground, allowing for less information to be leaked through the potential fluctuations. And since all of the attacks include a reference or require a reference to ground, physical mitigations require isolating the ground signal from any input-output port of the laptop, particularly effective for the cable extension attack. Also, they proposed a low impedance ground path to minimize the voltage drop on the chassis and to avoid switching voltage regulators. Lastly, they also mentioned a Faraday cage to limit the signal noise leakage, but that seems pretty inconvenient to put around a laptop. just for security purposes. So there's a few software mitigations as well for ciphertext normalization. Since this attack relies on modular reduction by padding since the ciphertext itself is usually padded with either zeros or something, or the public key to pad the length, the software can strip the zeros to prevent that from happening. The ciphertext can also be randomized, in which the text is multiplied by a random value r. The computations for the cipher is done, and then divided by r to get the same results. However, this, as it says here, won't fix the key distinguishing ability of the attack. So in the future, the authors proposed another thing as well, as once they cover their attacks, they just next thing to do is look for it. So is there a way to design switching power supplies to reduce computation noise coupling? And looking into software approaches to this hardware problem, is there a way to resolve the key distinguishing version of the attack that's still present even with the randomization for the ciphertext that we previously covered? And could this attack vector be applied or exploited without having the software controlling the PC? So yeah, some things to consider, and some pretty interesting attacks, although I think the testing methodology was a bit weak on this paper. The attacks themselves were very, very interesting, and we really did appreciate how realistic the authors made these scenarios for how this attack could go down in terms of their testing, or in terms of their testing setup and their like hypotheticals. So yeah, thank you all for listening to our presentation, and we'll take questions.
Great, thank you, Esther, and both of you actually. Yeah, so this is actually one of the first group of papers that it was like get off your hands of something. So it's like get off of your hands from my cloud, from my computer, from my cell phone. If you actually Google the word, you will see that there are, I think, 3 or 4 papers with the same kind of like naming convention. And then, yeah, you mentioned like, so one reason for not like, having an extensive test is usually like, academic papers like this is mainly just trying to show the feasibility of the idea rather than like having a very, well-versed testing strategy. That's usually, for the real attacker to to do it, but they're kind of like just mainly showing this. And then also for attack papers, people don't want to be looking too much evil-like, right? So they don't want to show that, oh, we actually tested on real systems and we attacked people and we went to coffee shop, for example, and extract information, right? So that's why you have to kind of like also be aware of those kind of things. All right, yeah, go ahead.
I was just gonna say that's a good point.
Yeah. Any questions in the chat from Zoom? I guess that's it. Thank you guys. Thanks.
For sure. Thank you. All right. Cool.
All right. So next is Naomi, Zayu. Are you guys there? I see Zayu.
Yes, we are here.
Okay. Can you are you gonna share your screens?
Can you guys see the screen?
Yes.
Oops.
You should do the slideshow.
Oh, okay.
Hi everyone, I'm Kun Xiang, and today I will present FPGA-based remote power side channel attack with Yu and Naomi. Let's get started with the problem statement. Nowadays, hardware acceleration is adopted in both cloud and mobile computing, which presses the demand for energy-efficient computing acceleration. Among them, field programmable gate arrays, which is FPGA, provide flexible hardware acceleration. Many companies utilize FPGAs for its flexibility through hardware-defined implementation of circuits on a fabric of reconfigurable logic blocks. For example, Amazon offers FPGA instances in its EC2 service, allowing customers to run FPGAs in its cloud computing environment. And Microsoft also heavily uses FPGAs in its data centers. But those integrated FPGAs are vulnerable for power side channel attacks, even without physical access or proximity to the target systems. An on-chip power monitor can be constructed using the programmable logic of an FPGA, allowing attackers to measure dynamic power consumptions with sufficient resolution to enable power analysis attacks. And these attacks include FPGA to FPGA power analysis attack and FPGA to CPU power-based timing attack. Power side channel attacks will infer confidential information based on the data-dependent variations in a target system's power consumption. Traditionally, for power analysis attacks, attackers usually require the physical access or control on the target system and then measure its power consumption. For example, they can insert a low impedance resistor in series with the power supply and use an oscilloscope to measure the power consumption as the voltage drop across the resistor. However, with the integrated FPGAs, the remote power analysis attack becomes possible. For the contribution they made in the paper, briefly, they found out a power side channel vulnerability of integrated FPGAs, which gives possibilities for remote attacks. They constructed an FPGA-based power monitor circuit using ring oscillators and demonstrated FPGA-based power side channel attacks, such as FPGA to FPGA and FPGA to CPU attacks. They can also be performed using another power monitor circuit-based delay lines. At the end, they propose potential solutions regarding the attacks. We will go through them in detail in next few slides. Assume there's no physical proximity to the target. We only build the power monitor purely through software on the fact that the propagation delay reflects the power consumption. This is because more power consumption results in more current flowing through the device, which then leads to the voltage drops in the power distribution network, as the formula shown. In CMOS circuits, propagation delays can be modeled to be inversely proportional to the voltage supplied to each gate. Therefore, a change in the delay reflects the voltage drop, which again reflects the power consumption and the switching activity of the circuits. So we can digitize these delay values using a ring oscillator. For a single RO as shown below, when enable is 1, we can see that for every oscillation, the output value flips. If we just simply look at output, it looks like a square wave. And if the power consumption increases, we can see the reduction in the supply voltage. And in turn, this changes the oscillation frequency. And if we connect the ring oscillator with the counters and let it run for, say, t seconds, we will have the digitized value of delays as shown. Therefore, an on-chip power monitor using RO is feasible. The constructed power monitor can be evaluated by characterizing the frequency change of the ring oscillators to a non-change in switching activity. They created a network of 20 RO circuits on a Z-board and take the sum of all RO counters as the final power monitor value. 16,000 instances of the power virus are instantiated on the FPGA fabric, and the results are shown below. We can see there is a linear field line that as the number of power virus or power consumption increases, RO frequency decreases. In this way, we know using FPGA-based power monitor to support remote attacks is possible. Next, Naomi will elaborate more on the threat model.
Okay, so first we start with the assumption that the adversary does not have physical access to the system, and therefore they cannot directly measure the power consumption. For the threat model, there are two types of attacks. First of all, we know that it's inevitable that sometimes FPGAs might be shared in some scenarios. For example, the data center architectures. In a shared FPGA, the malicious users may implement and attack circuits on one part of the FPGA in order to steal confidential information from a victim circuit on that same FPGA. We call this an FPGA to FPGA attack, which is shown on the left of the slides. We assume that the shared FPGA have common security mechanisms to ensure isolation between different users, or there's no illicit connection between the attacker and the victim modules. In the second case, we consider FPGA to CPU attacks where an attack circuit on the FPGA is used to extract a secret on a CPU or a GPU on the same SoC. We assume an SoC architecture that contains both FPGA fabric and traditional processing elements such as CPUs and GPUs as the picture that is shown on the right. For the FPGA to FPGA power analysis attack, the authors, they implemented a 1024-bit crypto engine on the FPGA that uses a algorithm called square multiply algorithm. This kind of algorithm iterates through all the 1024 bits in a for loop. The important thing in this algorithm is that looking at the if statement, if the condition is true, then the module has two multipliers computing at the same time. If the condition is false, we will only have one multiplier running, which would consume less power. They use the ring oscillator to record the power trace of running the program. Looking at the trace, we can tell that not only every round of the RSA decryption is visible, but also the actual bit value that is computed each round is also visible, which means that a simple power analysis or SPA attack is completely viable. We now consider two types of countermeasures. The previous work has shown that we can isolate the trusted and untrusted work physically by a logic block. The other method is to restrict the users from self-defined routing and placings. So there's like a less chance for the attacker to imply what they're doing on the FPGA. With the experiment results, it's proof that in either case, the attack is still efficient. By recording the automated SPA attack, when we have the control of the oscillators and the routing placing, it takes about 3.7 average traces to recover all the 1034 bits of all 10 cases. In the physical isolation case, which is ISO, the number increased to 8.9 traces for average. And the no placing and routing case, the number increased to 11.4. Next, we will have Zoe to talk about the FPGA to CPU power analysis attack.
Okay, let me discuss another FPGA attack, which is the FPGA to CPU attack. The SoC integrates many modules like CPU, DSP, and FPGA. In modern SoC, it's common that different modules share the same power supply. For example, CPU and FPGA's power supply are often shared. In this scenario, there are some potential security issues as FPGA can use power side channel to attack CPU. It's reasonable to assume that switching activity from CPU will cause a voltage drop that could be observed by the RO-based power monitor. By monitoring the power consumption, it is possible to know the timing information from CPU. Here's an experiment about FPGA to CPU attack. The CPU runs a simple string compare function where CPU generates 8,000 character string and compare this string to itself. The figure on the left shows a single power monitor output versus sampling count. It is obvious to see that power difference between it's obvious to see the power difference when CPU runs the function. The result also indicates that power analysis attack also revealed the execution time in the CPU. Let's see another experiment to evaluate the timing confirmation. The CPU input both long and short string to string compare function. It's also used the clock gate time function to measure the exact execution time. The figure on the right shows the histogram of the result. You can see a histogram of the execution time from FPGA monitor for long and short program execution. The two lines here represent the actual time from clock get time function. You can see the time difference between the actual time and the estimated time, which is related to the system call, but most time inside attack, most time inside channel attack are based on relative time difference in program execution. Besides RO-based power monitor, there is an alternative way to measure the power. Here's an alternative way on chip power monitor, which is the delay line.
Do you want to take a break, maybe a second, and then start?
I'm sorry. Here's an example. Here, you can see the example delay line here. It has the same principle as RO monitor, but delay line doesn't measure the propagation delay. The signal is passed through the chain, and after a fixed time period, the logic value of all nets are latched. The power consumption can be measured by observing the boundary between 1 and 0, since it's associated with the propagation time. To evaluate which method is better, there's a trade-off. The sampling period of delay line monitor can reach the clock frequency of FPGA. Well, the short sampling period in RO monitor will make the serious noise problem. Both power monitor have sufficient resolution to measure power change. For power resolution, it is difficult to say which method is better because there are RO monitor with many inverter has low power resolution than delay line with small wire delay. Well, delay line may have lower resolution than small RO monitor. One weakness of delay line is its circuit complexity and its sensitivity to placement and route, which means power attack based on RO monitor is easier to achieve in FPGA. Let's see some countermeasure to power attack. First, by inserting random noise or attacking, adding dummy operation or masking power consumption to high power signal. In this way, the SoC become more resilient against power side channel attack. But this countermeasure is always limited by overhead and energy. Second, for cloud FPGA service provider, it is necessary to check FPGA design to prohibit malicious design like FPGA power monitor. For example, analyzing the netlist to remove power monitor, and this allows user to define place and route to discredit the effectiveness of FPGA power monitor. However, doing such analysis will take a lot of time. We have some insight from this paper. First, remote power side channel attack is possible with integrated FPGA. Second, FPGA power monitor has low accuracy and resolution to may not work for discrete CPU and FPGA. Last, don't share FPGA to prevent remote attack from untrusted third party.
Well, let's think about what is the potential future work that we can spend more time investigating on. For example, RSA has been repeatedly given as an example of an algorithm which is susceptible to power side channel attacks. But is this a common exploitable property? Is it possible to focus on other representative algorithms? In addition, we can also consider other methods of monitoring activities. For example, does the real-world software always have parts that could be taken advantage of by monitoring power consumption? Last but not least, besides delay lines and ring oscillators, are there other structures in the standard FPGA that could be similarly exploited? This is the work cited, and thank you for listening.
You guys for the presentation. Any questions? Can you go back 2 slides? I think one was, so one of the suggestion, one more, yeah, on the insights. Yeah. So last one is not shooting FPGAs. Yeah, it's going, okay. Yeah, so I mean, the problem really is that it's hard to distinguish who is trusted third party and who is not trusted, right? So think about the business model of something like Amazon Web Services. They, like, and essentially anybody with an account and bank account can create a service there, and they can start using Amazon Web Services, right? So knowing who can be trusted and who's not is really difficult for a system like this. Of course, for more private systems you can, but for a system like this, it's very hard. So we are basically assuming that anybody can get access to those FPGAs. Solution really has to come from either at the circuit level or some sort of software level defenses. But yeah, it's a very interesting and innovative attacks, basically, showing that creating a bunch of ring oscillators and just looking at the delays of that can reveal some information. This is actually fundamentally caused by, as you guys mentioned, is fundamentally caused by the fact that most of the components on an SoC are sharing the same power management unit. And activity in one kind of like unintentionally leaked into the others, and people have shown many different ways of exploiting that, and this is one of the newer versions and more powerful versions, because essentially any remote user can program an FPGA, put some basic ring oscillators, and very quickly they can find this information. All right, any other comments, anybody? Okay, so let's have like a 3-minute break. We're gonna go back at 3:08. I'm gonna just switch to 2 presentations. So Pragya and Anusha are gonna go first, and then Sarah and John, if that's not an issue with Sarah and John. Right? Anusha and Pragya, do you want to start sharing your screen?
Should I share my screen?
Wait for a few more
Hi,
seconds.
my name is Anusha Arkell.
Oh, okay. Oh, you have the video recorded. Yeah, go ahead.
And my partner's name is Pragya Sharma. And today we'll be presenting the paper When LoRa Meets EMR, Electromagnetic Covert Channels Can Be Super Resilient. EMR is a classic exfiltration attack where the attacker steals classified data from a computer by using a malware to manipulate the EMR of memory, power management unit, USB, and so on. Conventional covert attacks hide data in network traffic, thus relying on a compromised network interface. In contrast, EM covert channels exploit the infiltrated computer as a radio transmitter and can bypass many security measures such as firewalls, traffic monitors, etc., and air gaps where network interfaces are disabled or removed. Previously, it was believed that shielding can protect from short-range EM covert channels. However, this paper debunks that idea and presents EM LoRa, a super resilient EM covert channel that can be decoded from hundreds of meters away and penetrate aggressive shielding. EM LoRa has a boosted communication range and attenuation resilience. There have been limitations surrounding prior attacks. The threat of EM covert channels is limited to short-range attacks due to the low power of EMR. This is an unrealistically close distance, which may defeat the purpose of being stealthy during an attack. EM signals are also at a risk of significant attenuation caused by shielding. Previous studies show that the EMR of CPU memory systems is only 15 decibels above the noise floor, which means the EM signal will be 85 decibels, or 2 times 10 to the 9th times weaker than noise after penetrating a Tempest shield. In comparison, Tempest, a standard developed by NATO and the US, requires sensitive systems to be protected by 100 decibels minimum. So the paper comes to the question, can EM covert channels survive deep attenuation? First, let's look at LoRa, a proprietary low-power, wide-area network modulation technique. LoRa, short for long range, allows for kilometer-range connectivity. LoRa features attenuation-resistant modulation called chirp spread spectrum. In each chirp, signal frequency increases linearly over time, leading to a pattern that can be significantly distinguished from significant noise. In LoRa, different Bs can be represented by different cyclic shifts of chirps. For example, the right figure shows 4 chirps, and the 2 bits represent one of 4 possible shift values. One of the fundamental questions this proposes is it feasible to exploit conventional EM sources as LoRa-like radios to fundamentally escalate the threat of EM covert channels? This leads us to EM LoRa, which was developed to examine the feasibility of this core question. EM LoRa is a super resilient EM covert channel which exploits memory as a LoRa radio transmitter. Experiments show that EM LoRa boosts communication range by 20 times and improves attenuation resistance by up to 53 decibels. However, to achieve this, there are some challenges that EM LoRa must overcome. From a signal processing perspective, EM LoRa faces the complex spectrum of memory EMR, and from a system perspective, the malware of EM LoRa faces signal distortions caused by CPU contentions, which poses a challenge for precisely shaping covert signals. Coming up, we'll look at how attackers can overcome these challenges to make EM LoRa feasible and reliable. EM LoRa's transmitter is a malware that shifts memory EMR by manipulating memory writes. The code of EM LoRa transmitter consists of 2 parts. The first part is a fixed frequency EMR generator, which writes 2 equal-sized byte blocks into memory, since the 2 byte blocks produce different current flow patterns in the memory bus. The generated EMR approximates a square wave, and the byte block size determines the wave frequency. The goal is to exploit the amplitude modulation effect of periodic memory activity to synthesize EM chirps. To generate chirps, a simple way of doing so is by calling the square wave method iteratively. But due to CPU contention, this results in EM LoRa being unable to accurately control the timing of the generated wave. This introduces frequency errors. To overcome this issue, EM LoRa performs approximate chirp generation. To do this, it first divides a continuous chirp into discrete frequency levels and then generates multiple square waves at each frequency level for a certain dwell time. The variance of average frequencies decreases as the number of square waves increases, which means the longer the dwell time, the stronger the EMR at the intended frequency. To generate a strong chirp, having a dwell time of 1.5 milliseconds is sufficient. It's important to understand the spectrum characteristics of memory EMR to decode the covert signal of EM LoRa. Before chirp modulation, memory EMR is purely produced by memory clock using spread spectrum to reduce EMR intensity. As shown in this equation, a memory clock is a sum of a series of subclocks. For example, the figures below the equation show the EMR spectra of DDR3 and DDR4. These agree with the model since the energy of memory EMR is distributed among subclocks, and these occur when the frequency is equal to f clock plus or minus n times f of m. Each peak in the figure corresponds to a subclock. When modulating EM waves, the ratio between jitter and wave period increases with EM wave frequency, resulting in more signal distortion. Therefore, at higher frequency levels, the jitter gets relatively amplified. The modulation of EMR introduces complex features into the spectrum of memory clock. This figure shows the power spectrum consisting of two EM chirps, synthesized by EM LoRa's transmitter. The chirp energy is dispersed as a series of mirror images where each subclock is associated with an up and down chirp. Each up and down chirp produce a sequence of harmonic chirp images. However, this energy dispersion significantly reduces the EM chirp intensity, which poses a challenge to the receiver of EM LoRa.
To decode covert EM chirps, EM LoRa augments the standard LoRa receiver to handle the complex spectrum of memory EMR. It performs a series of signal processing to fuse the dispersed chirp energy and boost the current signal intensity. The figure here shows high-level signal processing pipeline of EM LoRa. It first performs symmetric D-chirp, where it converts up and down chirps into fixed frequency signals. It then adds the result of these symmetric D-chirps and fuses the images of mirror chirp. To further fuse images associated with the subclocks, EM LoRa exploits the periodicity of the subclocks and performs folding. Folding is a signal processing algorithm originally used to amplify weak periodic signals in astronomical settings. After folding, the dispersed chirp energy is concentrated into a single energy peak whose frequency indicates the bits carried by the chirp. As a user space malware, EM LoRa transmitter has to share CPU with other processes. As seen in this figure, the CPU contentions of other processes may block the malware transmitter of EM LoRa, which interrupts the transmission of covert signals and distorts the generated EM chirps. To further understand the impacts of CPU contention, the authors test the effect of different CPU loads on frequency and power of EM chirps. As shown in the image on the right, EM chirps begin to suffer distortion when CPU becomes fully loaded. The frequency error and the power loss of the generated chirps further increase as the CPU gets overloaded. To help EM LoRa survive CPU contention, the trade-off between throughput and chirp robustness is leveraged. In particular, longer chirps carrying fewer bits improve robustness, but result in a decrease in throughput. On the other hand, shorter chirps carrying more bits decrease robustness, but increase the throughput. Based on this observation, EM LoRa first estimates the level of CPU contention and adapts the chirps to balance the bitrate and robustness. Specifically, it measures the timing errors experienced by the chirps and then uses it as a feature to classify the level of CPU contention. Based on the classification results, EM LoRa switches between three predefined spreading factors calibrated for underload, full load, and overload conditions. As you can see from the figure here, EM LoRa initially sends out shorter chirps in underload conditions, but quickly switches to longer chirps as the load increases. The authors created a prototype of EM LoRa's receiver using Blade RF, which is an inexpensive SDR, software-defined radio, equipped with a 2.2 dBi antenna. The malware transmitter is deployed on different systems equipped with DDR3 and DDR4 of different speeds. EM LoRa is compared with GSMEM, which is the state-of-the-art memory covert channel. It is observed that compared with GSMEM, EM LoRa improves attenuation by 53 decibels and extends the communication range by up to 21 times. When receiving from the DDR3 desktop, EM LoRa achieves a range of 2000 to 2050 meters and resists up to 78 decibels of attenuation. The resilience of EM LoRa can be further enhanced by using a high gain directional antenna, which can provide an additional gain of 70 decibels. In addition, the performance of EM LoRa is also evaluated under CPU contention with two different types of contending CPU workloads, namely video streaming and coin mining. The figures here show the performance of EM LoRa when the rate adaptation is on and off. It is evident that rate adaptation maintains attenuation resistance under CPU contention environments. EM LoRa is shown to also enable attacks in two previously impossible scenarios. By achieving long communication range, EM LoRa enables a wide area data exfiltration, which allows an attacker to deploy receivers in public areas and still receive classified data exfiltrated from a government building. To demonstrate this attack, a LoRa transmitter is deployed in said building, within concrete walls, and the receivers are placed at a distance of 30 to 1,000 meters from the building itself. It is observed that all packets can be correctly decoded at positions 1, 4, and 5, while the receivers at 2 and 3 experience moderate and severe packet loss respectively. Ray tracing based emulations are conducted in 2 scenarios where EM LoRa receivers are deployed near government buildings in Washington, D.C. and Beijing. In each scenario, 3 transmitters are placed within each building. In the case of DC, all the receivers are able to decode most packets with a loss rate of below 20%. However, receivers experience high packet loss for transmitter 2's packets in Beijing. This is hypothesized to be because of the concrete structure blocking the direct path between the transmitter and the receiver. In another experiment, the authors demonstrate through-the-wall data exfiltration from an aggressively shielded server in an indoor area. The target server is deployed in room D, and as you can see in the figure, and is shielded by a Faraday cage that provides about 70 decibels of attenuation. Without the Faraday cage, all receivers except one in room A are able to receive packets. On the other hand, when the Faraday cage is deployed, it turns the receiver B and I into dead spots. On the upside, all the other receivers are fairly resistant to the Faraday cage. In summary, this paper is the first super resilient EM covert channel, which explores memory as a covert LoRa radio. It offers significant improvement of attenuation resilience and communication range while enabling previously impossible attacks. EM LoRa can be explored in the future for other applications and EM sources. Thank you.
Thank you. Any questions? So either just talking about new type of channels for physical side channels, this was one of the examples, right? The idea is not just we like do some stuffs and unintentionally create EM side channels. A sophisticated adversary can basically create intentional modulations, including LoRa, and then the benefit of that would be extended range, better SNR, better bit rate, and things like that. So there are different metrics that the adversary can use. So like more and more you'll see these kind of papers these days that people have shown that beyond what we were expecting before, that yes, switching activities create side channels and people can leverage that side channels. This is like one step beyond that, and thinking about, okay, now given this fundamental issue, what we can do to make this even more vulnerable and more interesting in terms of attacks. And of course, on the flip side, the defense becomes more complicated, because not only we have to fix the original issue, and now we have to be worried about these kind of things. And specifically this paper, one additional thing that it's adding is, as the Anusha and Pragya was mentioning, the assumption that we have low range for EM, and then if we, for example, do shieldings, we can kind of at least contain the EM side channels. This paper is kind of like both of these assumptions are kind of like proven wrong in this paper, which means that now we have to think more about EM side channels and how we are protecting against them. All right. Okay. So any other comments, questions about EM LoRa? Cool. So let's do the last presentation for today. Sarah and Jot, are you guys here?
Yeah, I'll share my screen.
Okay. Did I say your name right?
It's Jot.
Oh, Jot. Sorry.
And Sarah. Yeah.
Okay. So Jot, go ahead.
Okay.
Welcome to our presentation on the paper Tempest Comeback, a realistic audio eavesdropping threat on mixed signal system on chip. I'm Sarah Willen, and I'll be going over the problem, background, and contributions. Then my partner Joe Verdi will finish up with the evaluation methods.
Can you guys hear it?
Yeah.
Okay.
Defense mechanisms, and future work. Imagine you're on a FaceTime call in your dorm room using your Xiaomi earbuds. Let's say you're planning a secret gift for another friend. What if your other friend could be listening in on your conversation from the outside of the room purely from interpreting the electromagnetic radiation leaks? Well, this is specifically the objective of the paper we are presenting today. Tempest attacks have a relatively long history starting in World War II and refer to those side-channel attacks where you can reconstruct plain data from devices that emit unintentional electromagnetic radiation. The significance of this attack is that it's a non-cryptographic attack where you directly obtain the plain data rather than first recovering the key to decrypt the secret information. In the 1960s, due to the complexity and specialized equipment needed to conduct a Tempest attack, it was considered only a nation-state level cyber attack for most of its existence, too sophisticated to experience on the local level. However, this was until the early 1980s when Wim van Eck used a $15 TV receiver to reconstruct a CRT screen from over 100 meters away. These days, due to limitations in attack distance, the Tempest attack wasn't considered its measured threat. However, this paper aims to contribute insight into a new form of Tempest attack that is relevant to our current technological climate. The paper discovered that because of the emerging switching regulator integrated mixed signal on chips, the Tempest attack is becoming a real and pertinent threat. So why is this new attack the focus? Well, it's because of the changing landscape of electronic device architecture that follows features of miniaturization and low power consumption. Miniaturization is where the mixed signal system on chip comes up. With increasing demands for smaller IoT devices, the mixed signal systems on chips contain digital, analog, and even power circuits and have applications in smart sensors, mobile devices, and medical device industries. The feature of low power consumption calls for increasingly integrating switching regulators into our systems. The audio signal resulting is coupled on the single common substrate of the mixed signal system on chip with the system clock and the switching noise. The paper posits that the root cause of the new audio-coupled EM leakages is due to the unavoidable integration of the switching regulator. This is because of the switching regulator's strong, low-frequency switching noises. The unique features of the new attack compared to the older are explained because, 1. The EM leakages have a dense frequency distribution, which means the periodic frequency intervals of the audio leaks are narrow. It is wideband, meaning the strong EM radiations exist from several megahertz to over 1 gigahertz. And third, the radiation is static opposed to carrier frequency hopping in the past Tempest attacks. These features allow the Tempest attack, due to the switching regulator noise, to have a longer attack range and to be more robust to interference. Next, I will introduce the threat model. The victim's device contains a mixed signal on chip. The paper tests the attack on many commercial devices, including a Xiaomi and Samsung earbud, among others. The adversary's goal is to listen in on audio information processes in a small audio IoT device without the owner finding out. The adversary cannot have direct access to the target device, nor needs to be even in the same room of the device. However, the attacker knows the characteristics of the device model. The adversary only has portable attacking equipment composed of readily available off-the-shelf components and antennas. Moreover, there is interference coming from commercially licensed frequency signals. Finally, the attacker must eavesdrop in real time. The characteristics found from this new attack prove threatening. First, the attack can occur at a long range, and the range can be increased more if an attacker combines the dense signals together. Secondly, the attack occurs in real time without the need of a cryptographic key. The attacker can also avoid interferences from commercial signals by altering the target frequency to a neighboring signal. This paper demonstrates that Tempest attack based on the switching regulated noise is a critical security risk by demonstrating that the EM radiation from commercially available audio IoT devices can be reconstructed at a distance in a real environment. Now my partner will go into explaining the experimental method and results.
So the authors conducted 3 types of experiments for this paper, and I'll go through each of them. The first one is done to gather results in sort of a controlled situation. So they started off in an echo-free chamber to see what would happen in sort of a perfect environment. The attackers would bring a large antenna connected to a laptop to store the signals. They then connect a microphone to the ADC port of the MSOC, which is a tier 3 MSOC in this case. And it's placed about 15 centimeters away from the antenna. Then the researchers play a frequency sweep into the microphone and the antenna picks up noise from the MSOC. So the MSOC used in this experiment has an option of using a switching regulator or a LDO. LDO, or low dropout regulator, is a voltage regulator that dissipates power into heat. Thus, it makes it less prone to leaking out noise compared to a switching regulator. The only downfall of an LDO is that it consumes much more power compared to a switching regulator. So by looking at this figure, it can be seen that the switching regulator exposes much more noise at a higher frequency as well. LDO only occasionally leaks out noise. So the only problem with the LDO is that it uses much more power, as I explained before. And we know how important battery life is when creating a portable device. Okay, so what about a bit more realistic scenario? The researchers, instead of playing a frequency sweep, they played a song called We Will Rock You by Queen into the microphone and recorded the noise coming out of the device when the switching regulator was configured instead of the LDO. Well, based on their findings, you could, not easily, but you could recognize the lyrics from about 5 meters away. And we won't be playing the sounds in this presentation because the quality is a bit rough, but if you click on the link right here, the Google Drive link, you could access the recordings. All right, now on to the second experiment. So this experiment is much more realistic compared to the first one. The setting in this one is an office environment with multiple everyday devices in the vicinity, like PCs and smartphones. The adversary has a setup as shown in figure 11. It's similar to the one in the last one, except the antennas are much smaller. So the device they're trying to attack is either a voice recorder or a pair of earbuds. And the device is connected via Bluetooth to a smartphone. So like the first experiment, the researchers play a frequency sweep into the earbuds or the recorder. So the most notable noise comes from the Sogu and the Xiaomi devices. The Sogu is a recorder and the Xiaomi device is a pair of earbuds. The rest of the devices actually illustrate that the attack isn't feasible from a realistic distance unless you're really close up. That's because the other devices use a hybrid approach of using both a low dropout and a switching regulator. And in some of these, it's not even known what regulator is used, and that's shown by type 3. So now you might be thinking, why are the Xiaomi earbuds still emitting noise, even though it's using both a switching and a low dropout regulator? Well, the authors concluded that the shape of the earbuds played a factor, and the earpieces are connected by a wire, which causes more noise to leak out through the system. The Sogu device is the only device that has a configurable switching regulator, and it can be seen that the noise from this device can be picked up from 13 meters away. On a side note, I kind of wish that the authors provided more experiments for a type 1 device because I think it would paint a better picture as to why a type 1 device is more susceptible to noise leaks. So how did the researchers get a signal from that far away, around 13, 14 meters away? Well, the devices actually emit 4 different types of signals that can be captured by adjusting the frequency of the radio receiver. And once the signals are captured, they're processed with a few techniques. So they used phase alignment, and then they summed up all the signals, and then they denoised the signal and used a few other techniques such as inverse fast Fourier transform. And then after that, they reconstructed the signal. So after summing up and cleaning up the signal is much stronger than only one signal. So far we've looked at devices that leak analog signals, but what about digital signals? Well, the researchers looked into that and they found out it's the same case. So they used a temperature sensor that uses the I2C protocol. They plugged it into the MSOC device and they read the temperature using an oscilloscope. They used the same setup as the last experiment where the antenna reads the noise from the MSOC device. And they were able to replicate the temperature signal as seen in part E of this figure. You can see that in part E, it matches up with part C, which is the temperature signal in bits. The only difference is the signal is inverted, but that's not really an issue. All right, how can we avoid these noise leaks from switch regulators? There's a few solutions in the paper to mitigate the noise. The first is to use a high input-output impedance device to reduce the current flow in the system. The only issue with this one is that if quality, let's say sound quality, for example, is an important factor, then the solution isn't really feasible. If signal quality isn't an issue, then this solution works great. The second solution is to use an electromagnetic shield that blocks out radiation. So the EM shielding uses a metallic enclosure to isolate the MSOC from its surroundings. So that way no noise gets out. The third technique is to apply line filters to the signal and power lines connected with the MSOC. So this one would be a good technique for the Xiaomi earbuds because the wires were causing a good amount of noise leakage. And the last solution is to avoid using only a switching regulator in the device. A hybrid approach with a low dropout regulator might be better as seen in the second experiment, excluding the Xiaomi earbuds, which is like a special case. As far as future research goes, we found a few things future researchers can look at based on the findings of this paper. The first one is to repeat the experiment with more type 1 devices and maybe find like an anomaly in the data because there was only one type 1 device used in this experiment. So just like how the Xiaomi earbuds were a type 2 device, they were supposed to leak much less noise compared to type 1. But in reality, they actually leaked a good amount of noise. There was also a lack of attacks done on digital devices. So maybe researchers can try other input modules instead of a temperature sensor and see if other devices have the same behavior as the temperature sensor. The last thing we'd like to see is to somehow replicate these attacks using smaller equipment. So as we saw in the figures in the beginning of the presentation, the antennas are quite large and the other equipment is not discrete. So I don't think it's feasible to carry around an antenna and receiver to eavesdrop on someone. All right, and that's all for our presentation. Thank you for watching.
Well, engineering change in negative ways in this in this presentation, right? So I mean, depends on who's using it, but yeah, thanks, Joe. Any questions, anybody? Yeah, I guess the takeaway from this was just paying attention to what brand we're purchasing, I guess, right? Because some are more leakier than the others. But I also seen a couple of other papers relevant to this that use, for example, the noise off of the ADC. So the idea there was, for example, we have a serial connection, SPI, or different types of serial communication between the analog world and digital world, right? What people have found was essentially the noise for the A to D and D to A can be measured, and depending on the activity of the processor, this amount of noise can be modulated. So for example, if a device is communicating with a central processor or microcontroller via, for example, SPI, what happens is the device can actually measure the noise, and based off that, for example, understand what the other microcontroller is doing. And for example, a recent paper I've seen that shows that they can even break the encryption systems of the host device. So yeah, generally this line of research of the noise that's associated with the power management unit, voltage regulator, and also the A to D and D to A's, which is kind of like from the same family, is interesting, and the people have shown that this is possible. And then going back to the first part of your presentation, all of these things happens again because we are integrating more and more things on the same substrate. So again, going back to the FPGA examples as we see it today, the trend really is that we want to save space, we want to increase the performance and decrease the cost and so on. But as we are doing that, this is actually we are making this system more susceptible to different types of attacks, right? And unfortunately, that's the trade-off that we are kind of paying, and we need to be also very cautious about this kind of optimization that we add to the system. Okay, any other questions or comments? This is kind of like concluding our discussions on physical side channels. Next week, what I'm going to do is talking a little bit about cyber physical systems, and then jump into more pure hardware security. So things like hardware trojans, piracy, and these kind of areas that are also quite interesting. So as I said, we started from top level algorithms, systems, and now we're really deep into the hardware. And that's where we're going to finish. All right. So if there's no other questions, have a great day, and see you guys hopefully on Monday. Hopefully I'll feel better. I'll update you if the class will going to be in person or on Zoom. The default is that it's going to be in person, right? All right. Thank you.